Okay, we're going to go ahead and move on. Our next speaker is Alberto Bolatto. Let me get in. He's going to be talking about gas galaxy surveys at z=0 to study galaxy evolution.
Interesting. My virtual background seems to be doing funny things, but
it makes your eyes red.
Yeah, let's try that. Okay, well, don't know what is happening, so you have to put up with that. But let me share my screen. Can you see it?
Yes, we can see it.
Good. Okay. So the topic here is to talk about galaxy surveys of the nearby universe, and particularly the role of the GBT. So I'm going to start with the big questions here, and I have some of the big questions on the right. So let me just say that all these questions in general relate to this particular diagram. That is a diagram of star formation rate on the y-axis against a stellar mass of a galaxy. So each symbol that you see here in the diagram is one galaxy, and they are color-coded by their amount of star formation activity. No? So the blue galaxies are actively star forming, the red galaxies are not. And so what you see, for example, is that there is a sequence here that is fairly tight, called the blue sequence of galaxies that are actively star forming. And then there is this red cloud of galaxies that are not over here in the bottom. So, one of the questions is what determines a blue sequence? I mean, clearly the blue sequence is some phenomenon of self-regulation, but precisely what are the physics and what are the mechanisms that have to do with this self-regulation is one of the questions that we want to be able to answer. Now, I mean, you will know that galaxies grow in mass as they age. Of course, they are forming more and more stars, so they have to displace toward the right in this diagram. But somehow they do keep moving along the main sequence if they are actively star forming. So how do galaxies evolve in this diagram is a question. And what is the importance of secular evolution versus, for example, merging, and what happens with AGN activity? So these are all things that we need to understand in order to understand how the present day universe comes to be and what are the properties that it has. So now in between the blue sequence and the red cloud here, there is this intermediate region called the green valley. And clearly galaxies at some point must abandon the blue sequence and evolve down. And the question is, how do they turn off? And why do they turn off? But particularly how? What happens inside a galaxy when they turn off and go into the red cloud? And then once you have it in the red cloud, well, can you revive the galaxy in any way, or is there something that is keeping galaxies off once they get into this state where they are not forming stars? So you will notice that all these questions are truly questions about what is happening with the gas in galaxies. And the reason for that is that, the y-axis here in this plot relates to us, no? So you are converting particularly dense gas into stars, and that's what gives you the star formation rate. So to answer these questions properly, we absolutely need radio surveys, and particularly millimeter wave surveys. So that's fundamental. No? We cannot figure out what happens with galaxies and their evolution without radio surveys. So what is the state of the field in that? Well, I mean, we traditionally, we have taken two approaches, and I'm talking particularly about millimeter wave surveys here, so molecular gas surveys. And so you have spatially unresolved surveys on the one hand, and of course they are easier to do because you just do one pointing per galaxy, and it's easier to get a larger number of galaxies. But the drawback of that is that the only thing you get are average quantities over the galaxy. No? However, because they have large numbers, they have shaped our view of what gas in galaxies is doing. So here are a couple of examples, the FCRL survey being, for example, one of the primary surveys. And here are the numbers of galaxies that you can get using this technique. So 300 galaxies, several hundred galaxies in the other. On the other side, we have spatially resolved surveys. And the interesting point is that once you do spatially resolved observations, you get a lot of internal information about the galaxy And it has been argued that this internal information is fundamentally what you need to resolve ambiguities about what type of processes are leading to the evolution. In other words, if you use galaxies as test particles, there are a number of things that you cannot answer, but once you resolve them into systems and they have an internal structure that you have to explain, then you get way more information about the problem. The other side, of course, is that these are much costlier surveys. So you have a number of examples here. And one thing that I want to highlight is that it's only very recently that we're getting into the 100 territory for the number of objects into these surveys. By contrast, spectroscopic optical surveys are more in the 1,000 to 10,000 galaxy territory. So we're far behind in the radio. The other thing that I want to highlight is that several of these large surveys coming from single dishes are made possible by array technology. We wouldn't be there if it wasn't because of array technology, array receiver technology. So what is the role of the GBT here? Well, I mean, let me just say that for this particular purpose, the GBT is an awesome survey machine. So on the right, what I have done is I have done the same plot of star formation rate versus galaxy mass. And I'm just plotting in blue, all the galaxies within 50 megaparsecs in a particular database. And in red, things that are big enough and northern enough that they are interesting to map with the GBT. So I'm selecting galaxies that have an optical diameter greater than 2 arc-minutes and a declination more northern than minus 15 degrees. So those are 1,200 galaxies. The resolution that we will get in CO with the GBT would be about 6 arcseconds. And here are a number of things that you can compute with what efficiency you can do this with Argus. But the bottom line is that you can do pretty fast mapping at very good sensitivity with Argus in this particular case. And so these numbers over here for RMS sensitivities are very, very interesting if we compare them with other things that are in the literature and that have been done. And that's for Argus 16, so Argus plus, however number you want to put in there. Of course, it's going to be even faster depending on the size, on the footprint versus the size of the object. But this looks very, very good. So I think the GBT could be helping us answer all these questions that I was posing before and making strides on this topic right now with Argus 16 and even better in the future with Argus 144. So it's nice to say that we're going to answer the questions, but what do we really mean? What are the specific experiments? So let me give you just a few concrete examples. So this is one of the possible experiments that you can think of running. So here you have a plot of metallicity versus gas fraction for pixels inside galaxies. And gas fraction is just the ratio of gas to the ratio of stellar mass in a piece of a galaxy. And the data are, well, the beams of data here are in the blue symbols. The data, the locus of the data is the contours. And essentially, this particular plot is comparing two evolutionary models that have two different hypotheses. And these are the gas regulator model and the leaky box model. And the comparison to the data, trying to fit the trajectories of these models to the data, what it gives you is essentially a handle on this parameter lambda, which is how much gas you put out in outflows versus how much gas you put into star formation. So it's an interesting parameter. It's a mass loading of outflows in galaxies. So just to note a couple of things about this particular experiment, I mean, this comes from optical spectroscopy. So you need complementary data in optical spectroscopy. In this particular version of the experiment, this was all done with optical data. So what the authors did here is to convert extinction into molecular gas because they have extinction for a lot of galaxies. So that's what they have done. And in reality, we would like to put real gas data in that axis. No? So this is where the role of radio surveys comes in. And the last point is that, of course, these numbers, we want to span a large dynamic range. And what that really means is that we need sensitivity, and the GBT gives you the sensitivity that you need to do this very well. There are many other examples that you can come up with, for example, about tests for inside-out quenching, etc., of galaxies. How do galaxies turn off? But this is just one of them. Another type of experiment that you can think of doing with this type of data is fundamentally, comparisons to simulations, observations versus simulations. And, simulations have taken a while to incorporate variance on cosmological scales, but they are getting there. So they are actually being more and more powerful in their predictive power for what is going on with baryonic physics on cosmological scales. Yet people who do the simulations still benchmark them mostly against optical data because there isn't all that much gas data to go around. So we can provide that information that is missing. And here is an example of a comparison of some measurement that comes out of the simulations that you can do, which is a ratio of the size of the galaxy in molecular gas versus the size of the galaxy in stars. And the blue will be what illustrious TNG gives you versus what we measure in the real universe. And that's the histogram for Karma Edge. So, this is key information to the people who are doing the modeling, because if you reproduce things well or you don't reproduce things well, in this case seems to be more of the latter, that people have to understand what is that they have to change in the simulations to do things better. So I have a couple more slides. One of the things that I want to bring up is this dichotomy on how do you go about putting together a survey? How do you think about what type of objects you want to go after? And there is always this tension between going for very nearby galaxies where you can get the high spatial resolution and mass sensitivity. But of course, that limits you to a lower number of galaxies on the one hand. And going for a larger volume sample. And so let me just bring up something that people don't necessarily think about, which is that if you were arguing, like Peter was arguing in the previous talk, well, you need to resolve individual GMCs. That's very limiting in how far you can go out, and that's that's interesting for particular goals. No, so if you are gearing your survey toward understanding a particular detailed mechanism, you may choose to do that and go to a very high resolution. When you do a large volume survey, you pay the price of lower mass sensitivity and lower spatial resolution, but what you gain is the population behavior, because you are sampling over a larger number of galaxies and fundamentally larger number of conditions. So we are not all that used in the radio to think about cosmic variance, but cosmic variance exists, no, for us too. And that is just the impact of environment. So every time you do a survey that is very local, you're essentially sampling the local environment, and you're not sampling necessarily an environment that is, is a common environment across the universe. No? For example, we're very close to the Virgo cluster, so we end up doing always a lot of Virgo galaxies. Is that the right thing to do or not? Clearly, you're sampling something very peculiar. So that's how much that impacts is difficult to evaluate on observations, but you can do that in simulations. And here is a comparison of what you get for just a very easy parameter that you can get out of the simulations, the ratio of molecular gas to stars in a galaxy, and what you get when you sample over a small volume, which is the red histogram, and over a much larger volume, which is a blue histogram. And what you see there is the impact of cosmic variance. Each one of those small volumes is doing a great job at sampling its local conditions, but it's only its local conditions. So let me just close by bringing up these three conclusions. I think Argus, or Argus 144, have a huge role to play in extragalactic surveys. I think we have been doing a survey, and Amanda is going to talk about that in the next talk, which is the gap. But we started with the harder proposition of doing lines that are much fainter. They're in a better part of the atmosphere, but they are much, much fainter than CO, for example. So we have learned that the performance on CO is good, And I think it makes a lot of sense to do large surveys in CO because of everything that I have been talking about. We always, of course, have to compare to other machines around, and we should compare to ALMA. So why are we going to do this in the GBT if we have ALMA? And I would point out that, as I always point out when I try to compare a single dish to an interferometer, that interferometers are great at doing high resolution, but they are not great at recovering spatial structure that is extended. No, so ALMA goes through a lot of contortions to recover the extended spatial structure. All of us who work with ALMA know that how difficult that is. And the other point is that the sensitivity that you have is low because you don't have all that much collecting area that is sensitive to the large scale. So by comparison, a single dish, you can average things straightforwardly. There is no problem in recovering a bunch of things and increasing the sensitivity by doing spatial averaging. And finally, the point that I started with, I mean, we need these surveys to answer key open questions in galaxy evolution. So, that's what I wanted to bring up to you, and I'm happy to answer questions if you have any. Thank you.
Thank you, Alberto. I just had a question in terms of the recovery with the ALMA observations of nearby galaxies. What fraction does ALMA recover? Is it 30, for CO especially, is it only 30% or 50%?
So what do you mean by what fraction does ALMA recover?
Of the single dish fluxes? I don't know if people have made those comparisons with 30-meter data or whatever. And some of them.
So you're saying if I only use the 12-meter array and a particular configuration, the 12-meter array, what fraction would I recover? And that depends on the particular configuration and on how far the object is. But I think the proper way to look at this is to say, what collecting area does ALMA have that is sensitive to scales of several tenths of arc seconds, for example? And the answer is that's a collecting area of the ACA.
Yeah.
So you're not comparing with 50 12-meter dishes. You are comparing to a handful of 7-meter dishes. So that's a ratio of collecting area you have to think about when you're talking about extended structure.
Thank you. That's a good point. Let's see here in the Q&A, there are no open questions, but in terms of for the galactic, I mean, the extragalactic projects, one could argue that we don't need Argus 144. We could get by with an Argus 64 for a lot of galaxies in just terms of matching the field of view of the instrument with the population of nearby galaxies. I mean, there's trade-offs there. So I don't know if we could, for extragalactic work, one could argue maybe we want to go with more bandwidth and also look at ways to pack the horns in closer together and that kind of work potentially.
So let me say a couple of things. I mean, of course, the more you pack the horns closer together within the limitations of the technology, the better off you are,
Yeah.
Because the fundamental thing that you're against is that there are only so many galaxies that are given that have a size that is bigger than something. So that's what you have to think about. But so the precise question of how many galaxies can you do efficiently with Argus 144 versus Argus 16 depends on the distribution of sizes of nearby galaxies. And I haven't done that particular calculation. Several of these 1,200 galaxies are bigger than these 2 arc minutes that I put in. So for those galaxies, you will be more efficient. Of course, the majority of galaxies are going to be at the 2 arc minute limit, no? So in that case, you have no advantage with a bigger array. I mean, there are some advantages in calibration, etc., with a bigger array, but they are not, necessarily all that much more efficient.
Yeah.
So yeah, this is something that has to be thought through, and maybe some flexibility. I mean, a lot of this is correlator flexibility. Maybe sometimes you only want to use the inner part of the array and have much more correlator capability for those pixels.
Yeah, that makes sense. Put in the bandwidth on the inner part of the array. Okay, Well, thank you very much, Alberto. I think we're going to move on to our next speaker.